Hello, class. Okay, so we're going to continue talking about circular motion, but we're going to talk about how we would apply Newton's laws of motion. So first off, let's review. We talked about, so I'm going to write down here, Newton's laws. Newton's second law in particular, net force equals mass times acceleration. And again, this is a vector equation. So what we've been doing in chapter 4 is we introduce a coordinate system. So we have an object and we make an XY coordinate system. And what we have is F net. I'm going to do this. We'll use sigma notation. So that's Newton's second law. And this is equivalent to two scalar equations, where when we break things up into x and y components, this is equivalent to the net force in the x direction is mass times acceleration in the x direction. And the net force in the y direction is mass times acceleration in the y direction. Now, we could have a z direction as well, and again, we just have net force in the z direction is equal to mass times acceleration in the z direction. Now, what we're going to do to describe circular motion is we're going to have a different coordinate system. We're going to break up our coordinate system differently. We're going to have different directions here. So let's say we have a circle. And say we have an object that is, moving counterclockwise. So our counterclockwise is basically the standard. And so what we're going to do is we're going to break our coordinate system into components like this. We're going to have a radial direction and a tangential direction. And we could also have a z direction as well. So this is an object moving in a circle. Maybe it's moving in like a horizontal circle. And so if you look at it from a different perspective, it's moving in a circle like this, where again, that's horizontal, but it would just look like a line. But anyways, we could have, like, say this is the radial direction. The tangential direction would be like into the board. And we'll call up the z direction. So like this is the xy plane. So we could have a z direction as well. So again, just different perspectives. Like this is looking down on this circle. So we have radial direction. Tangential direction is the direction that it's moving. And z direction would be upwards. So if we rotate this so that here's the ground, the z direction is upwards. So what we have for let's just talk about circular motion in general. Again, we can break this up. We can say that the net force in the radial direction is mass times acceleration in the radial direction. And the net force in the tangential direction is mass times acceleration in the tangential direction. And we might also have the net force in the z direction is mass times acceleration in the z direction. So we're using Newton's second law. We're just breaking up our vectors into components in a different way now. And it's a little different because like this direction here, like if you look at a different point, these directions would change. So So they change as we're moving around, but we always have like a radial component and a tangential component. Now, for a moment, let's just stick to uniform circular motion. I'm just going to call that UCM, uniform circular motion. You know what? I don't want to actually do that. Let's just call it circular motion in general. What we have is the net force in the radial direction. That'd be mass times acceleration in the radial direction. But again, the radial direction is outwards. And remember, the acceleration is always inwards with a magnitude of v squared over r. So for circular motion, the net force in the radial direction is always minus mv squared over r. And then the other two equations, we leave them alone. However, well, here, let's look at the net force in the tangential direction. That's mass times acceleration in the tangential direction. And if we're in uniform circular motion, this would be equal to 0. So this acceleration in the tangential direction, or that's a direction of velocity. The velocity is in the tangential direction. So if we have an acceleration, that's going to be the particle either speeding up or slowing down. So, yeah, uniform circular motion, constant speed, that means there's no tangential acceleration. So very often, in most cases, this equation is going to be the net force in the tangential direction is 0. We usually don't even bother writing that one down. And then, net force in the z direction equals mass times acceleration in the z direction. Again, very often that one's going to be 0. Not all the time. So I think what we'll do is we'll look at 2 examples of circular motion. And maybe I'll just do one. Probably my favorite example. So I want to do that one for sure. I think I'll leave one for actual... there's kind of 2 good ones we can do. I'm going to leave one for class. So we'll do 2, but one of them, I want to talk about a car on a banked curve. So this is actually kind of an interesting problem. You might have seen these before if you're driving. Now, of course, if you're on level ground, a car wants to go straight. The inertia is trying to cause it to go straight. If you want to turn, you need friction to do that. Friction between the tires and the ground to be able to make the turn. And if you're going too fast, you're not going to be able to stay on the road. Another issue could be, the weather. If the roads are icy, try to turn. If you don't have friction, the car can just go perfectly straight. I've had that happen before, where you hit the brakes and it's like the car just doesn't even care that you hit the brakes. It just keeps on going. So, yeah, so you might have seen these where you have a banked curve. And, we're going to look at a problem, basically, how would we design a banked curve? So, we have to imagine a car, like there's a speed limit for this road. Like you're supposed to take the curve at a certain speed. So let's say we have a car on the banked curve, and let's start with that. What forces are acting on the car? Well, first off, we have gravity straight down. And we have a normal force. Now, friction also plays a role here. And what role would friction play? Well, say the car wasn't moving at all. What's it going to do? It wants to slide down the incline. And so friction would oppose that, and it would be pointed in that direction. Now, what if the car is moving very fast? It's going to want to go up the incline. Picture, like, say you have a marble in a bowl, and you spin it, the faster it goes, the higher up in the bowl it wants to go. And so if a car is going fast, it's going to want to go up the incline, and then friction is going to cause it to go downwards. So if you're going slow, here, let's see, if you're going slow, friction is going to point in this direction. If you're going fast, friction is going to be down the incline. Either way, though, friction is going to help keep you on the road. So what we can do is we can design this banked curve for a particular speed, where if there was no friction at all, you can make this curve just by going that speed. You won't slide up or down the incline. And so, we're going to design a curve. We want to find out what angle to bank this curve so that you can take this at a constant speed. Now, if you're not going exactly that speed, friction is going to help either way. If you're going too fast or too slow, friction is still going to help. Okay, so what we're going to do is we're going to solve this problem pretending friction does not exist. So we're designing it for a particular speed where we would not need friction at all. So let's say that we have a particular speed in mind. Let's say 30 meters per second. And let's say the radius of this curve is 200 meters. Now, obviously this doesn't have to be like a complete circle. It could just be a portion of the circle. So the circular motion would only be happening over a fraction of the circle, but yeah, that's fine. So our goal is to find the angle. And so what we do, we're going to use the same rules that we've been using in Chapter 4, except our coordinate system now, again, the car is going like this way. The center of the circle, say, is over here. So this is our radial direction is outwards. And our z direction is upwards, and the tangential direction is into the board. However, we're moving in a constant speed, so we don't care about the tangential direction. We're not even going to bother writing that down. So, step 1 was identify the forces. We've done that. Step 2, pick our coordinate system. And then step 3 is let's look at our forces and determine, which ones are in the coordinate directions, and if they're not, then we have to break them into components. So let's redraw here. We've got gravity. That one is perfectly fine. That's in the minus z direction. We're good there. However, the normal force needs to be broken into components. So first, let's draw a few lines here. So, this line is parallel to the incline. That makes this angle theta, which makes this angle theta. And that makes this angle theta. So again, let's say this is 30 degrees. That's 30 degrees. And again, this is the incline, and this is the normal, which by definition is perpendicular. So if this is 30, this is 60. And again, these two lines are parallel, so they have to add up to 90. So if that's 60, that's 30. Same as our incline angle. And so if we break the normal force into components, the z component, that would be cosine. That's adjacent. So here we have Fn cosine theta. And then in the radial direction, we have Fn sine of theta. Okay, so we finished that step. We drew a free body diagram with our forces in the coordinate directions. And the next step is to apply Newton's laws. So to start out with, we're going to look at the radial direction. And this is going to be a recurring theme in this chapter. And after a while, we're going to get sick of doing it and stop. But we're going to just go with it. The net force in the radial direction. So the radial direction is to the right, and the force is to the left. So we have minus Fn sine of theta. And that's equal to minus mv squared over r. And this recurring theme I'm talking about is we're always going to have two minus signs which cancel each other out. And again, we'll get in the habit at some point of just neglecting to even bother writing down the minus sign. But for now, we'll just keep writing it down, knowing that we're going to ignore it later. Okay, now nothing's going on in the tangential direction. We ignore that. And then in the z direction, we have Fn cosine of theta equals mg. Or we could write Fn cosine theta minus mg equals 0. Let's do that. We'll clean it up later. So these are Newton's second law, just in component form. It gives us two scalar equations. So Fm sine of theta, minus. So like here, the net force in the z direction is Fn cosine of theta minus mg. And again, the acceleration in the z direction is 0. The z direction is vertical. The car isn't moving up or down vertically. It's just going around in a circle. And so now let's kind of clean this up a little bit. Let's get rid of this minus sign. So we have Fn sine of theta equals mv squared over r. And here Fn cosine of theta equals mg. So we just, top equation, we just got rid of the minus sign on each side. And in the bottom equation, we moved mg over to the other side. So what we're trying to do is find the angle, theta. So what we know are the velocity and the radius, and we want to find theta. Now that might look a little difficult here because we have like sine of theta and cosine theta. There's various ways we could solve this. Some fairly complicated. There's one very trivial way to solve this, though, where we can basically do it in one step. Let's divide these equations. Let's take Fn sine of theta and divide by Fn cosine theta. And so Fn sine of theta is mv squared over r. And Fn cosine of theta is mg. So a lot of things happen here. One, the normal force cancels out. And on the other side, the mass cancels out. And sine of theta over cosine theta is tangent of theta. And what we have left is tangent of theta equals v squared over gr. Now, something very important happened here. Notice that this angle does not depend on the mass. And that's very important because if you notice on the road, there are vehicles of very different masses. You have like ordinary cars. You could have those huge tractor trailers that are the size of many cars. You could have motorcycles or even smaller, those little smart cars. But yeah, you have a huge variety of masses. But again, they should all be, the same road should be able to handle them regardless of the mass. And so, like we have the velocity and we have the radius. One thing I will note here, velocity squared would have units, meters squared per second squared. g is meters per second squared, but then times the radius in meters. And so, yeah, tangent of theta just gives us a number. Very important that it does that. Okay, yeah, why don't we just plug in the numbers? So v squared, that'd be 900. And then divided by 9.8 times 200. And again, if you're doing this on a calculator, you want to be very careful that you use parentheses here. Otherwise, your answer will be crazy. But anyways, that's around 0.46. So the inverse tangent, and for this example, theta would be around 24 degrees. Again, regardless of the mass of the car or truck or motorcycle or whatever, they'll all go the same speed over this curved road, this banked curve. Now, one thing I should point out that when you look at problems like this, we're treating a car as kind of like an object. Now, you might notice different cars kind of behave differently. Like, if you have some cheap car and you're going very fast and try to take a turn, that might be very dangerous. Where if you have a BMW or something, it can handle that turn easily. And again, that's not really something that's showing up in our equations. And the reason why is our equations are simplified. We're treating a car as just an object. It's like a mass, and there's a certain amount of friction between the car and the ground. And that is not actually very realistic, because a car is not just a rigid object. It has a suspension system. So like the tires can move up and down relative to the car. And so that could be a very big factor in how the car handles turns. So if this doesn't kind of match up with your real world expectations, there's a reason for that. We're simplifying things. It'd be much more difficult to model a real car with a suspension system. But to a good approximation, though, we can just treat a car like an object. Okay, and there's one more problem that I want to do because I really like this problem, and that is something called a conical pendulum. So I'm going to try to draw this, and I'm going to consider kind of like a low-speed pendulum. So the idea is if you tie a mass on the end of a string and kind of just swing it around, it's going to move in a circle. Now, if you swing it really fast, it's going to appear to move in a horizontal. Well, it'll appear like the string will be horizontal. It's not perfectly horizontal, but the faster it goes, the more horizontal the string is going to become. But I want to consider like a kind of a slow speed, so we have something like this. So the object is moving in a horizontal circle, but the string is making an angle. So let's say we have a string with a length L. Let's say L is 1.1 meter. And say this object is moving with a speed of, say, 6 meters per second. That's kind of, let's say 4 meters per second. So we want to know a couple things. Let's give it a mass of, say, 70 grams. So what I want to know is the tension in the string and also the angle of the string. Let's define that angle. We could also draw a horizontal line and have a horizontal angle here. But again, if you know one, you know the other. Like if that was 20 degrees, that one would be 70. You can pick whichever one you want. Okay. So again, it's moving in a circle. This would be the center. So again, this would kind of look like a, if we drew it, it should just be a line. But we draw an ellipse. You have to kind of use your imagination to kind of see this. I guess maybe we're looking kind of downwards on it. But anyways, we want to, let's find the tension in the string and the angle that it makes. So, to start with, let's look at step one, identify forces. Like here's the ground. So we have gravity acting straight down. And there's also tension in the string, and that's all that's going on here. Gravity and tension, these are the only two forces acting on this pendulum. Oh yeah, the name Conical Pendulum, you can see it's going to like sweep out a cone as it goes around the circle. Okay, so the next step is our coordinate system. That's our radial direction. And upwards is our z direction. So we have our kind of standard coordinate system. I can do this. Mass is 70 grams. We'll put that up here. A little more room for our coordinate system. Okay, so now the next step, let's look at our forces and see if they need to be broken into coordinates, or components. So if we look at, here's our mass, gravity's fine. That's in the negative z direction, but tension has to be broken into components. Now, if we draw like this vertical line here, this angle would also be theta, and so that's the vertical component of tension, or the z component, that's adjacent to the angle. So that would be t cosine theta, and this one is t sine theta. So we have a vertical component, that would be, say, tz, and that would be tr. So we broke tension up into a z component and an r component. And now we can write down Newton's second law. Where again, we're going to annoy ourselves with this minus sign because the radial direction is outwards, tension is inwards. So what we have is minus tr, or minus t sine of theta, is equal to minus mv squared over r. Yeah, I think I might have to change this problem a little bit, but let's continue. If we look at the z direction, we have t cosine of theta minus mg equals 0. And I think I might have made this problem a little more complicated than I intended it to be, because we have to find r. Like we have L and theta, so we can say that I think it might be better if I just give you the radius. Then that would define this angle. Let's kind of go with this. So let's see if we can actually solve it without making it overly complicated. But again, we set up the problem. Now the thing is, we don't know what r is. We know from this triangle here, sine of theta would be r. This is the radius of the circle. So sine of theta is r over L. And so let's see what we can do with this. So we've got Newton's second law, and we have this additional equation here. Okay, so let's see if we can solve this. Let's see if we can find this angle. So first off, let's rewrite this without the minus sign. So we have t sine of theta equals mv squared divided by r, which is L sine of theta. Yeah, I wonder if this is going to be solvable just mathematically. And then we have t cosine theta equals mg. So what we have is t L sine squared theta equals mv squared. And actually, I think we might be able to solve this. So this is probably a little more complicated than I would... Oh, wait, no, there might be a problem here. Oh, let's see if we can do it. Okay. And t cosine theta equals mg. I thought I saw a trick, but that's not going to work. But let's look at this equation. T cosine theta equals mg. We can say cosine of theta equals mg over t. And let's make a triangle here. So here's our cosine, or here's theta. So cosine of theta would be mg over t, like this. And what we could do is we can use the Pythagoras Theorem and find that other side would be m squared g squared minus t squared. So again, if we square this side, we get m squared g squared, and, oh yeah, square root here. And then if we square this side, we get m squared g squared minus t squared. Oh, I think I got that backwards. Should be t squared minus m squared g squared. So if we add these, if we square this, we square them both and add them, yeah, we'll get t squared. So we can say sine of theta is, here, let's say sine of theta would be the square root of t squared minus m squared g squared divided by t. And then if we square that, we have TL. So sine squared theta so this is getting oh yeah, we do not know what the tension is. So we're not even done here. We have a little bit of cancellation here. Oh wait, can we solve for t now? So what we know the length. We know mg and we know velocity. So yeah, this turned out to be messier than I intended. I'm going to check the notes for a minute. I think, oh, I didn't even put this in the notes, which I should have. Although I think, yeah, there's a suggested problem here. Conical pendulum. We have, yeah, so there's a suggested problem that has a conical pendulum where I give you the length of the string and the radius. And so that makes things a lot easier. So basically, we did solve this, you know, without me giving you the radius, because we can solve this equation for t. Just have to make some room for it. So since we're this far, we might as well finish it. But if I give you a conical pendulum problem on homework or an exam, I'll give you that radius so you don't have to go through all this algebra and stuff like that. But let's erase that. Let's work with this. We can cancel out one of the t's. And so let's divide by, here, let's move this t over here and divide by L. So what we have is t squared minus m squared g squared equals mv squared t over L. Now it looks like we have a quadratic equation. So yeah, this is definitely a nightmare. We can do it, but yeah, like we have our coefficients where a would be 1, b would be minus mv squared over L. We've got all those. And c would be minus m squared g squared. So yeah, to find the tension, we'd have to either try to factor it. No, we can't do that, I don't think. Yeah, so we'd basically have to plug this in a quadratic equation to get the tension. And then once we have tension, then we can solve for theta using, like, say, this equation. So this is a solvable problem, but by not giving you the radius, that made things a lot more complicated than I intended. But let's leave it here. I mean, here we, in a sense, solve for tension. What I would do here is calculate these coefficients and then just plug them in a quadratic equation. And yeah, once you get tension, then finding the angle would be fairly easy. Cosine of theta would be mg over t, and then take an inverse cosine. So I don't want to actually plug in the numbers, so let's just leave it like this. Sorry, I made this problem a little more complicated. I should have just read the suggested problems. There's a reason I give you the radius, even though technically it's not needed. But I guess it didn't hurt to do it this way as well. So yeah, we'll go through some examples, more examples of circular motion and how we'd apply Newton's second law. It's the same procedure as before, except now we're just breaking it up in a different coordinate system. So I think we'll leave this one here. So that'll be all.